April 2025. Imagine a faint, almost imperceptible flicker in the glow of a distant red star, like a candle wavering in the cosmic wind. This subtle dimming, caught by the keen eyes of astronomers, whispers something extraordinary. A signal. A clue. At precisely 012, researchers announce a potential biosignature from a world over 100 light-years away. A spectral fingerprint of dimethyl sulfide, DMS, in the atmosphere of the enigmatic exoplanet K2-18b. On Earth, DMS is a gas almost exclusively produced by living organisms, drifting from ocean phytoplankton into the salty air. Could this be the scent of life wafting across the stars? If confirmed, this discovery, announced at 035, could be the most compelling hint yet of biological activity beyond our solar system. The news ignites headlines worldwide, sparking a question that echoes in every curious mind. Has the James Webb Space Telescope truly detected the chemical aroma of life on a far-off planet? At 052, in the vast silence of space, a new chapter in humanity's quest for extraterrestrial life begins to unfold. But before we leap to cosmic conclusions, we need to set the stage. What kind of world is K2-18b? What makes this distant planet so tantalizing? Let's embark on a journey to uncover the mysteries of this captivating exoplanet, a speck of wonder orbiting a faint red star. K2-18b orbits a cool red dwarf star, K2-18, nestled 124 light-years away in the constellation Leo. Picture a crimson sun, smaller and dimmer than our own, casting a gentle glow over this alien world. First spotted in 2015 by NASA's Kepler Space Telescope during its K2 mission, K2-18b revealed itself through tiny dips in its star's light, brief shadows cast as the planet crossed its star's face. From these fleeting eclipses, scientists pieced together its essence: a planet with a radius 2.6 times that of Earth and a mass 8.6 times greater. This places K2-18b in a fascinating category: a sub-Neptune, or mini-Neptune, larger than our home but smaller than the icy giants Uranus and Neptune. It's a world that defies simple comparison, neither a rocky Earth nor a gas giant, but something intriguingly in between. What makes K2-18b even more compelling is its orbit within the star's habitable zone, that cosmic sweet spot where temperatures might allow liquid water to pool on a planet's surface. A year on K2-18b flashes by in just 33 days, a swift dance around its dim star. Yet, because of the star's faintness, K2-18b receives a similar amount of stellar energy as Earth does from our Sun. Its estimated average temperature hovers around 265 Kelvin, or about 17 degrees Fahrenheit, chilly but potentially Earth-like depending on the strength of its greenhouse effect. Can you imagine a world where oceans might shimmer under a red sun's glow, cradling the possibility of life? This planet's allure deepened in 2019 when the Hubble Space Telescope detected water vapor in its atmosphere, a groundbreaking discovery. For the first time, scientists confirmed water vapor on a small exoplanet in the habitable zone, a finding that sent ripples of excitement through the scientific community and beyond. Water, the elixir of life as we know it, suggested K2-18b hosts a substantial atmosphere, perhaps rich with clouds or mists. This revelation cemented K2-18b as a prime target for further study, a beacon in the search for habitable worlds. Could this be a distant cousin of Earth, or something far stranger? As observations piled up, K2-18b began to defy categorization. It's not quite an Earth-like rocky planet, nor a gas giant like Jupiter. Instead, scientists propose it might belong to a newly defined class of worlds called Hycean planets, a term coined in 2021 by researchers at the University of Cambridge. The name, Hycean, blends hydrogen and ocean, painting a vivid picture of planets cloaked in deep oceans beneath hydrogen-rich atmospheres. These worlds, larger and more massive than Earth, often with radii 2.6 times ours and masses up to 10 times greater, could still harbor temperate surface conditions. Imagine vast, reflective seas stretching under a hazy, hydrogen-veiled sky, a world both familiar and utterly alien. As we linger on K2-18b's mysteries, the stage is set for deeper exploration. What secrets does its atmosphere hold? How does its environment shape the possibility of life? To answer these questions, we must dive further into the data and the science, peeling back the layers of this distant world. Let's turn the page and continue our cosmic journey, exploring what makes K2-18b a beacon of hope in our search for life among the stars. Picture a world where endless oceans stretch beneath a thick, hazy blanket of hydrogen, a planet unlike anything we've ever seen. K2-18b fits this profile almost perfectly, earning its title as a prime candidate in our cosmic quest for life. But what would a Hycean planet, this so-called ocean world, truly be like? Imagine a realm where seas plunge hundreds of miles deep, cradled by an atmosphere dominated by hydrogen, perhaps laced with helium. Unlike Earth's nitrogen-oxygen air, this lightweight atmosphere stretches far into space, a gossamer veil that insulates the planet like a cosmic quilt. At 452, scientists describe how this hydrogen-rich blanket could trap heat, keeping those vast oceans liquid and teeming with potential. Could such a world, orbiting a faint red dwarf, hold the key to life as we know it? Hycean planets like K2-18b are thought to be surprisingly common in our galaxy, especially among subneptunes of this size. For years, these mid-sized worlds were overshadowed by the search for Earth-like rocky planets. But at 521, the tide is turning. The potential of Hycean worlds is forcing astronomers to rethink the boundaries of habitability. As Niku Madhusudhan, an astronomer at the University of Cambridge and lead author of the discovery paper, notes at 539, these findings highlight the need to explore diverse habitable environments. Traditionally, the hunt for life focused on small, rocky planets. But Hycean worlds, with their thick, observable atmospheres, offer a golden opportunity. At 608, their expansive, hydrogen-heavy skies make it easier to probe for signs of life across vast distances. Could these ocean giants be our best shot at detecting alien biology? To unravel K2-18b's true nature, we must dive deeper into its structure, piecing together clues from its size and density. With a density of about 0.1 pounds per cubic inch, K2-18b isn't purely rocky like Earth, nor a gas giant like Jupiter. Instead, at 644, models suggest a layered world, a cosmic onion of sorts. At its heart lies a rocky core of silicates and metals, glowing faintly with residual heat. Above it, immense pressures transform water into exotic forms, creating a mantle of high-pressure ice. And beyond that, if conditions align, a vast liquid ocean might sprawl, an endless sea with no land in sight, stretching under a hydrogen-dominated sky. At 722, K2-18b emerges as a global ocean world, a planet where waves might lap under a crimson star's glow, encased in a thick, hazy atmosphere. But does this ocean truly exist? The answer hinges on the thickness of K2-18b's hydrogen atmosphere. If it's too dense, the water below could be crushed into a strange, supercritical state, neither liquid nor gas, but a hostile fluid unfit for life as we know it. Yet, if the atmosphere is thinner, more modest, the water might form a true liquid ocean, perhaps mirroring Earth's life-friendly seas. Early studies at 812 suggested K2-18b's water might be locked in this supercritical state, with no clear ocean surface. But newer data from the James Webb Space Telescope, analyzed at 819, paints a different picture. The atmosphere may not be as oppressive as once thought, hinting at a genuine ocean atmosphere boundary, a liquid sea beneath the gas. One clue lies in the absence of ammonia. At 843, scientists expected ammonia in a hydrogen-rich atmosphere, but its scarcity tells a story. Ammonia dissolves easily in water, and a liquid ocean would act as a perfect sink, pulling it from the air. The James Webb Space Telescope detected methane and carbon dioxide in K2-18b's atmosphere at 901, but the low ammonia levels strongly suggest a deep, liquid ocean below. Picture it, an abyss deeper than Earth's Mariana Trench, possibly warmed by the planet's internal heat and atmospheric insulation. This ocean could be a cradle for life, its depths hiding secrets we're only beginning to explore. As we marvel at K2-18b's potential, the journey is far from over. What other clues lie hidden in its atmosphere? How do its oceans and skies interact to create a world so alien yet so promising? Let's turn to the next chapter, where we'll probe deeper into the data and uncover what makes K2-18b beacon in our search for life among the stars. Deep beneath a canopy of thick, misty clouds, where a humid, hydrogen-rich atmosphere meets cooler layers of space, K2-18b hides its secrets. At 9:26, we imagine a world where vast oceans churn under a sky unlike our own, their depths shrouded in mystery. But what lies beneath these waters? As we dive deeper, the pressure transforms liquid water into exotic, high-pressure ice, potentially forming a barrier between the ocean and the rocky core below. At 9:37, this icy layer could stifle the flow of minerals from the planet's depths, limiting nutrients essential for life. Could life still thrive in such a challenging environment? Perhaps it resembles Earth's deep-sea creatures, thriving in darkness, drawing energy from chemical gradients or the faint, filtered glow of a distant red star. For now, these ideas remain tantalizing speculation. At 10:08, our knowledge hinges on one remarkable tool, the James Webb Space Telescope, JWST, a cosmic detective sniffing out the chemical makeup of K2-18b's atmosphere. How does it work? At 10:35, JWST's infrared spectroscopy captures the molecular fingerprints of distant worlds, revealing their secrets. Every 32.9 days, K2-18b passes in front of its star, letting a sliver of starlight filter through its atmosphere. At 11:12, molecules in that atmosphere absorb specific wavelengths of light, leaving dark lines in the spectrum, like a cosmic barcode. By splitting this starlight into a rainbow and studying the missing pieces, JWST decodes the chemistry of K2-18b's air, painting a vivid picture of its alien skies. This method, called transit spectroscopy, was first used by the Hubble Space Telescope to hint at water vapor on K2-18b. But at 11:44, JWST takes it to new heights with its superior sensitivity and broader wavelength range. The results? Stunning. By late 2023 at 12:02, JWST confirmed clear signatures of carbon-bearing molecules in K2-18b's atmosphere, methane and carbon dioxide, glowing like beacons in the infrared spectrum. These findings marked the first solid evidence of atmospheric composition on a sub-Neptune in the habitable zone. Methane dominates some wavelength bands, CO2 others, suggesting a hydrogen-rich atmosphere brimming with these gases. Water vapor, expected at 12:29, appears in trace amounts, possibly locked in high-altitude clouds or mist, adding to the planet's enigmatic allure. But the real intrigue lies in what's missing: ammonia. At 12:46, its near absence, combined with the presence of methane and CO2, strengthens the case for K2-18b as a high-ocean world with a liquid ocean below. But ammonia dissolves easily in water, and a deep ocean would soak it up, leaving little in the air. Scientists visualized this in a transmission spectrum chart at 13:02, where a blue line maps the best fit for JWST's data. Prominent absorption features, highlighted in purple, red, and green, reveal methane's presence, while a tantalizing dip at 3.3 microns hints at something extraordinary: dimethyl sulfide, DMS. Could this be the chemical whisper of life? At 13:36, this spectral spike doesn't quite match expected molecules, except for DMS. After running atmospheric models, scientists reported at 13:51 a.m. possible DMS detection, though with low confidence. On Earth, DMS is tightly tied to life, produced by ocean phytoplankton wafting their chemical signature into the air. At 14:04, this faint signal is enough to spark global excitement, but caution remains. The data isn't conclusive, yet it's a tantalizing clue, a breadcrumb in the cosmic hunt for alien life. As we ponder this distant ocean world, questions swirl like clouds in K2-18b's skies. What does this DMS signal truly mean? Could it point to life? Or is there another explanation waiting to be uncovered? Let's journey forward to page 4, where we'll explore the implications of this discovery and what it means for our search for life among the stars. Imagine peering through the James Webb Space Telescope, its infrared gaze piercing the cosmos to reveal a world 124 light-years away. At 1421, JWST's data, spanning wavelengths from 1 to 5 microns, paints a vivid portrait of K2-18b, a hydrogen-rich atmosphere swirling with methane, carbon dioxide, and, most tantalizingly, a possible trace of dimethyl sulfide, DMS, a molecule tied to life on Earth. This discovery, announced at 1433, marks a historic first, a unique chemical cocktail detected in the habitable zone of a distant star. Picture K2-18b's skies, thick with gases, hovering above a vast ocean. Methane and CO2 abound, ammonia is scarce, and at 1459, a faint whiff of DMS hints at something extraordinary. Could this be the chemical signature of alien life? These clues suggest an atmosphere interacting with a liquid ocean, possibly influenced by biological processes. But how convincing is this cosmic story, and what makes DMS so special? At 1517, the buzz around DMS stems from its profound connection to life on Earth. This pungent sulfur compound, with its briny, cabbage-like scent, evokes the salty tang of ocean breezes near blooming phytoplankton. At 1544, these tiny marine organisms, phytoplankton and bacteria, produce a compound called DMSP to regulate their cells. When they die or are consumed, DMSP breaks down, releasing DMS into the air. On Earth, nearly all atmospheric DMS comes from these oceanic life forms, with negligible contributions from non-biological sources like volcanoes or hydrothermal vents. At 1625, this makes DMS a powerful beacon. Detecting it is like stumbling upon campfire smoke in a forest, a sign that something, or someone, is present. Could K2-18b's DMS signal point to a thriving alien ecosystem? What makes DMS even more intriguing is its fleeting nature. At 1704, sunlight breaks it down in days to years, meaning a steady source must replenish it to be detectable. If K2-18b harbors DMS in measurable amounts, as suggested at 1720, something on that planet, perhaps a biosphere in its deep oceans, is actively producing it. For astrobiologists, this is a thrilling prospect, hinting at life beneath a crimson sky. Adding to the intrigue, the methane detected at 1737, alongside CO2 and the absence of ammonia, strengthens the case. On Earth, methane can be produced by microbes, though at 1755, non-biological processes like hydrothermal reactions could also explain it. But the combination of methane, CO2, and no ammonia is harder to sustain without life. At 1811, methane tends to break down under stellar radiation unless a robust source, potentially biological, replenishes it. Now, layer in the tentative DMS signal, and the story becomes compelling. At 1827, this chemical trio paints a picture of a dynamic, possibly life-supporting world. Yet, extraordinary claims demand extraordinary evidence. At 1837, the DMS detection remains unconfirmed, a faint whisper rather than a shout. Scientists approach it with healthy skepticism, urging caution. But the signal's low confidence level means other explanations, like rare chemical reactions or instrument noise, can't be ruled out. At 1850, this balance of excitement and restraint keeps the discovery grounded, inviting us to dig deeper into the data. As we stand on the edge of this cosmic mystery, K2-18b beckons with unanswered questions. Is the DMS signal a true sign of life, or could it be a cosmic red herring? What challenges lie ahead in confirming this discovery? Let's turn to page 5, where we'll unravel the cautions, explore alternative explanations, and dive deeper into the quest to understand this distant ocean world. The excitement surrounding K2-18b's potential biosignature is like a cosmic campfire, warm with possibility but tempered by caution. At 1908, researchers remind us that the evidence for dimethyl sulfide, DMS, remains inconclusive, a faint flicker in the data. The signal, detected by the James Webb Space Telescope, JWST, carries a statistical significance of just 3 sigma, meaning there's a 0.3% chance it's merely noise. In scientific terms, as noted at 1927, 3 sigma is intriguing but falls short of the gold standard, 5 sigma, where the odds of a random fluke drop to a mere 0.000000003%. Imagine trying to spot a single star through a stormy sky. JWST is pushing its limits, sifting through faint signals buried in cosmic static. At 1946, astronomers commenting in Nature's coverage of the discovery highlight this challenge, noting that the data is noisy, and what one team sees as a molecular signature, another might dismiss as random fluctuations. Could this tantalizing hint of life be a trick of the cosmos? At 2005, detecting these signals is no small feat. Picture starlight filtering through K2-18b's thin atmospheric veil, 124 light-years away, carrying whispers of its chemistry. Instrument noise, data processing choices, and the star's own activity can mimic or mask these signals. At 2018, an independent reanalysis of JWST's 2023 data, conducted by another team, found no clear trace of DMS or other biosignature gases, suggesting the initial hint might be a statistical artifact. The spectrum, described at 2045 as quite noisy, underscores the difficulty of pinpointing molecules across such vast distances. Adding complexity, JWST's data at 2056 suggests the signal could stem from DMS or a related molecule, dimethyl disulfide, DMDS, which shares similar spectral fingerprints at certain wavelengths. At 2106, DMDS could form through chemical reactions, like DMS oxidizing or bonding. If DMDS is present, the case for life shifts slightly. On Earth, it's produced by some plants and bacteria, but at 2141, it can also arise non-biologically through photochemical processes involving sulfur compounds. The current data can't definitively distinguish between the two. Perhaps the biggest hurdle is ruling out non-biological sources for DMS itself. At 2157, lab experiments and models show that certain chemical processes, like organic compounds exposed to high-energy radiation in comet-like or primordial environments, can produce DMS without life. In 2024, at 2221, researchers at the University of Bern, Switzerland, detected DMS in the coma of Comet 67P/Churyumov-Gerasimenko, studied by the European Space Agency's Rosetta spacecraft. At 2230, this icy, lifeless body released DMS among its chemical emissions, proving the molecule isn't exclusive to life. This discovery casts a shadow of doubt, suggesting K2-18b's signal might have a non-biological origin. Then there's the star itself. K2-18, a red dwarf, is no quiet bystander. At 2307, its flares and star spots add another layer of complexity. Flares unleash ultraviolet radiation that can alter atmospheric chemistry, breaking down molecules like methane or DMS or creating false signals. At 2323, star spots, cooler, dimmer patches on the star's surface, can distort transit spectra. If K2-18b passes in front of a star spot, the light's signature shifts, potentially mimicking or obscuring the planet's atmospheric signals. At 2341, JWST's analysis tries to account for these effects, but it's a cosmic puzzle with missing pieces. Until we gather more transits or, ideally, confirmation from other instruments or telescopes, the DMS signal remains a tantalizing possibility, not a certainty. As we linger on K2-18b's mysteries, the line between hope and evidence blurs. Is this distant world truly whispering signs of life, or are we hearing echoes of cosmic noise? What steps must scientists take to confirm this discovery? Let's turn to page 6, where we'll explore the next phase of this cosmic journey and what it means for our search for life among the stars. The faint whisper of life on K2-18b hangs in the balance, a cosmic riddle waiting to be solved. At 2400 hours 07, the next few years will determine whether this tantalizing signal strengthens into a clear beacon of alien life or fades into an intriguing anomaly. Picture the distant red dwarf K2-18, its flares and flickers shaping the story of its orbiting world. Understanding this star, its flare frequency, spectral quirks, and age, is crucial as it profoundly influences K2-18b's habitability and how we interpret its data. At 2400 hours 24, scientists are meticulously sifting through JWST's findings, planning new observations to confirm the atmosphere's composition. But their gaze extends beyond today's tools, toward a future where next-generation telescopes promise to unravel K2-18b's secrets with breathtaking clarity. What might these cosmic lenses reveal about this distant ocean world? At 2400 hours 44, the coming decades will usher in observatories far more powerful than JWST, transforming tentative clues into concrete discoveries. Scientists are already dreaming of missions like LUVOIR and HBX, visionary space telescopes proposed by NASA for post-2035. At 25:07, LUVOIR envisions a colossal mirror stretching up to 16 yards wide, more than twice the size of JWST's 7-yard reflector. Imagine this giant, gathering starlight like a cosmic net, capturing finer details of exoplanet atmospheres. At 25:35, LUVOIR could snap direct images of worlds like K2-18b and produce ultra-detailed spectra, while HBX, designed as a dedicated planet hunter, would wield a star shade, a massive shield floating thousands of miles ahead to block starlight, letting the faint glow of nearby planets shine through. At 25:55, this would reveal the dim radiance of worlds orbiting stars like our Sun or smaller red dwarfs, scanning their atmospheres for signs of life. What could these telescopes do for K2-18b? At 26:16, their larger mirrors would collect more photons during each transit, sharpening the signal-to-noise ratio of the spectra. If JWST stands at the edge of detection, LUVOIR could confirm DMS's presence, or rule it out, with unwavering certainty. At 26:50, these missions would also probe a broader wavelength range, from ultraviolet to deeper infrared, beyond JWST's reach. This could unveil new biosignatures, like ozone in ultraviolet or organic hazes at shorter wavelengths, painting a richer picture of K2-18b's atmosphere. Even more exciting, at 27:14, these telescopes won't be limited to transits. They could directly image some exoplanets, capturing their faint light. For K2-18b, orbiting close to a dim red dwarf, direct imaging is a challenge, but at 27:44, a large infrared telescope might detect its thermal glow as it passes behind its star, offering another way to map its atmosphere and surface temperatures. Beyond LUVOIR and HBX, other missions will join the hunt. At 28:02, the European Space Agency's Ariel, set to launch in 2029, will study the atmospheres of hundreds of exoplanets, including candidates like K2-18b. Though less sensitive than JWST and focused on shorter wavelengths, Ariel could refine measurements of known gases and spot subtle changes over time. At 28:20, this collective effort, space-based and ground-based observatories, will bring sharper focus and a wider lens to our cosmic exploration. These next-generation tools promise to transform our view of K2-18b and countless other worlds, turning whispers into shouts. As we stand on the cusp of this new era, K2-18b remains a beacon of possibility, its secrets just out of reach. What will these future telescopes reveal? Could they confirm a thriving biosphere or uncover new mysteries? Let's turn to page 7, where we'll explore the broader implications of this journey and what it means for humanity's quest to find life among the stars. K2-18b isn't a solitary puzzle in the vast cosmic tapestry, it's part of a grander quest. At 28:47, scientists plan to study a fleet of exoplanets with similar sizes and temperatures, searching for patterns that could unlock the secrets of life. Imagine if dimethyl sulfide, DMS, appears on multiple Hycean worlds. Wouldn't that suggest something universal, perhaps biological, is at play? At 28:54, such a discovery would strengthen the case for life across the cosmos. But if DMS is found only on K2-18b, as noted at 29:02, it might mark this planet as uniquely special, or reveal the initial detection as a cosmic fluke. Either way, K2-18b has become a cornerstone for exoplanet science, a beacon guiding our search for answers. At 29:12, this distant world marks a turning point, challenging decades of chasing Earth's twin, a rocky planet orbiting a sun-like star. K2-18b, with its larger size, lack of land, and orbit around a dim red dwarf, shatters that mold, expanding our vision of where life might thrive. At 29:39, this ocean world invites us to ask bolder questions about life in the universe. It's not just about finding another Earth, it's about casting a wider net, from rocky planets basking in sunlight to subneptunes cloaked in hydrogen around red dwarfs. At 30:04, K2-18b pushes us to consider biosignatures beyond oxygen and ozone, embracing exotic compounds like DMS that might hint at alien biology. Picture a future, a century from now, where a Starship probe, powered by advanced AI, embarks on an epic journey to K2-18b. At 30:22, as it nears the K2-18 system, its cameras capture a shimmering blue orb bathed in the rosy glow of a red dwarf star. At 30:36, the probe confirms our suspicions, a planet swathed in thick clouds, hiding a vast ocean below. Descending through a hydrogen-heavy atmosphere, it parachutes through skies painted red by filtered starlight, buffeted by winds fiercer than Earth's storms. At 30:50, it pierces the cloud layers, sampling their chemistry, until it reaches an alien ocean stretching endlessly to the horizon. At 31:06, under the faint glow of a crimson star, half the size of our sun, smoldering like an ember, the ocean's waves glint with coppery light. As the probe dives into the dark, boundless depths, it discovers microbial life, a revelation at 31:24 that confirms we are not alone. Yet, such a mission lies far beyond our current reach. At 31:30, the 124 light-year gulf to K2-18b dwarfs today's propulsion technology, leaving us as distant observers, decoding faint spectra and refining theories. Each transit, each spectral line, brings us closer to understanding this world. At 31:48, our telescopes, JWST and its successors, stand as vigilant sentinels, listening for whispers of life across the void. What if those whispers grow louder, revealing a universe teeming with life? As K2-18b's story unfolds, it sparks new questions about our place in the cosmos. How will our understanding evolve with each new observation? What other worlds might hold similar secrets? Let's turn to page 8, where we'll explore the broader impact of K2-18b and the next steps in humanity's quest to find life among the stars.